As it turns out, the second derivative can actually tell us something useful about extrema as well. This leads us to the second derivative test. It is for finding local extrema. So the second derivative test is going to use the second derivative to classify extrema. So I find the domain, the first and second derivatives, locate the critical values. So these are first order critical values, because there are places where the first derivative equals 0. Now, unfortunately, the second derivative test is not built for places where the first derivative fails to exist. That type can only be classified with the first derivative test. If the first derivative is equal to 0, I can substitute those critical values into the second derivative, and then if the second derivative is concave up, it's going to imply a minimum. So if the second derivative is positive, it's going to imply a minimum. And if it's concave down, it's going to imply a maximum. Okay? So this test does the same job as the first derivative test. So similar job to the first derivative test. You want to keep in mind that it's not a similar job to the test for concavity, which also uses the second derivative. So there are three tests: the first derivative test, the test for concavity, and the second derivative test. The first derivative test and second derivative test are the two that are similar. This is not similar to the test for concavity. It also classifies extrema. Its goal is to classify extrema, which is the same thing that the first derivative test does. It tells us if we have max or mins. It does not, however, tell us about increasing and decreasing. Alright, so again, what it does, like I drew up here, if the first derivative is equal to 0, that means that you have a critical value. If you have a critical value where the concavity is positive, it must be a minimum. That's what we saw in part A. If you have a critical value where the concavity is negative, that critical value must be a maximum. Okay? Alright, at the bottom we have a summary. We can tell a lot about a function by examining analytically its first and second derivatives in our summary right here. First of all, if f is differentiable on an interval, differentiable means that it's going to be smooth on the interval. So there are no sharp changes to this. It's no peaks, nothing sharp. It's all differentiable, it's all smooth. If the first derivative is greater than 0, then your function's increasing on the interval. If your first derivative is less than 0, then your function's decreasing on the interval. If f prime changes sign, so it changes from increasing to decreasing, that's going to be one of your two extrema, depending on how the sign changes. It's either a local max or a local min. Okay? So these three boxes deal with the first derivative test. So I'm going to label those three. Those three boxes deal with the first derivative test. Okay, then we have that if the first derivative is equal to 0 and the second derivative is positive, you have a maximum. If the first derivative equals 0 and the second derivative is, sorry, that was negative, so you get a maximum. Positive, you get a minimum. And I have my minimum. So those together are the second derivative test. Okay, which we just saw on this page. They do the same job, classifying extrema. Then the other thing that we talked about so far in this section is if the second derivative, trying to read the second derivative is greater than 0, it talks about concavity, concave up. Second derivative less than 0, concavity, concave down. Second derivative changing sign, inflection point. And so those three things together were the test for concavity. Alright, that puts together a summary of all of the tests that we saw in this section at least. We saw a test for absolute extrema in a previous section, so we've got lots of tests right now. Okay, now we're going to use the second derivative test to do something, and a helpful trigonometric identity, it looks like, to do something here, to locate the extrema to this function. Okay, so in the second derivative test, I need to begin with the domain, similar to what we've begun with before. So the first thing I need is the domain. Luckily, sin of x has domain of all real numbers, and when I square it, I'm going to stay at all real numbers, so the domain is all real numbers, but we have a restriction. So we're going to use that restriction that we're not looking at the full sine wave, we're looking at the restricted domain of 0 to 2 pi. Okay, so we look for domain restrictions, sometimes we have them. Alright, so I've got my domain restriction. Then the next thing that I want to do is find the first and second derivatives. So first for derivative, remember that that original function is written in shorthand notation. So this original f of x function is really the sine of x function quantity squared. That square on the sign is shorthand for this. And so if I do the derivative, I'm going to use the chain rule. So it's going to be 2 times sine of x times the derivative of sine of x, which is cosine of x. Okay. Then we're going to want the second derivative, which at this point would require the product rule. So the second derivative is going to be 2 times, I'm going to leave the sine of x function alone, take the derivative of cosine of x, that's negative sine of x, plus the reverse, plus 2 times the derivative of sine of x is cosine of x, and I'll leave the cosine of x alone. So it gives us negative 2 sine squared of x plus 2 cosine squared of x. Okay, so I've got my first and my second derivative. Next, we need to look at the critical values. So we're looking at first derivative being equal to 0. Okay, so 2 sine of x cosine of x equals 0. It's a product, so I can set the product equal to 0 by parts. So I can either have sine of x equals 0, or I can have cosine of x equals 0. And on a unit circle, if sine of x is equal to 0, that's my y coordinate. So we're going to be equal at 0, pi, and 2 pi. We're going to go all the way back to 2 pi because the interval is closed. Then cosine of x is anywhere the x coordinate is equal to 0, so that's going to be at pi halves and 3 pi halves. So I've got a lot of critical values here. Now, in this case, if I was going to use the first derivative test, I would have to partition my interval 1, 2, 3, 4, 5 times. So I have 6 different intervals and 6 different test values. So it would make that table rather large. That's one small advantage of using the second derivative test in this case. Then in step 4, we want to plug these values into the second derivative. So we're going to evaluate f prime, double prime at 0. I'm going to try to put them in order. So at pi halves, f double prime at pi, f double prime at 3 pi halves, and f double prime at 2 pi. Can evaluate all of these. Now, I don't care what the actual value comes out as, I just care if it's positive or negative. Okay, so I'm going to use Desmos to plug these in. There we go. So the second derivative, I'm just going to call it g of x. And it's equal to negative 2 times the sine of x squared plus 2 times the cosine of x quantity squared. Can we type? Okay. So I don't need to see the graph. I'm going to turn that graph off for right now. And I'm just going to evaluate it. So I need g of 0. And so that's 2. I need g of pi divided by 2. I need g of pi, g of 3 pi halves, and g of 2 pi. Okay, so I see positive, negative, positive, negative, positive. All right, so if I flip back my screen, these are positive, negative, positive, negative, positive. Now, the conclusions. Okay, so the conclusions from step 5 are that we have a local minimum at any place where the derivative was positive, because these ones were concave up. Concave up means minimum. So we have a local minimum at x equals 0, pi, and 2 pi. And we have a local maximum at x equals anywhere the derivative was negative, because derivative negative means concave down, means maximum. So at x equals pi halves and 3 pi halves. Okay. Looking back at our picture, we can hopefully confirm this. So at 0, pi, 2 pi, we see those local minima, and at pi halves and 3 pi halves, we see those local maxima.